Okay, so welcome to the second lecture. So maybe let's start with a small recap of what we discussed yesterday. So yesterday, well, we mostly spent the first lecture on giving some general introduction, general definition. So the objects that we want to compute are scattering amplitudes with loops. So Feynman diagrams with loops. And this leads us to the notion of a Feynman integral, which is an integral over a loop momentum and some propagators. Okay, so this is what we said yesterday. And I just want to highlight here a couple of things, which is that, first of all, we looked at it in 4 minus 2 epsilon dimensions, and let me even write it as d0, where d0 is an even integer number. It could be 4, but I could even consider integrals in other dimensions. I could also do it in odd dimensions, however, then some of the properties are different. And the other feature was that we allowed for arbitrary exponents, integer exponents. And well, the reason for this was that in this way we can see our integral as defining a point with integer coordinates on a lattice. And so for every point on this lattice, there's an integral. For a given graph, okay? So I have a certain, maybe that's the point that I should stress more. So if I take a Feynman graph, each edge in my graph defines a propagator. Okay, so like this propagator could be q1 square minus m1 square. This propagator could be 1 over q2 square minus m2 square, and so on. So this is a Feynman graph. For each such graph, I have an infinite family of integrals, which are distinguished by the choices of these exponents. Okay? Remember that I also allow these exponents to be 0, which means that the propagator is absent. And I even allowed the exponents to be negative, which means that these propagators appear in the numerator. In this way, I can also consider integrals with numerators. So those are the basic definitions that we considered. And what we said is, okay, there are two challenges when you want to compute these guys. First was challenge number 1 was call it combinatorial. With just the number of diagrams that you need to compute, or the number of integrals. And the other one is doing the integrals. And we started to look at this challenge here, the combinatorial one, where we said, okay, so how can we find the basis? And the idea was look for recursions on this lattice Zn. And the way to find these recursions was via what's called integration by parts identities. Which were based on the fact that in-dimensional regularization, the integral of a total derivative is always 0. And then we use the fact that if you differentiate propagator, then you get something that is proportional to equals 1. So the theorem tells you that integrals of total derivatives gives you 0, but in this bracket here, you have propagators of this type. So when you act with a derivative of what is inside the bracket, we will produce other propagators, but with shifted exponents. And in this way, you get recursion relations between different points in this lattice. And so that is what we had. Sorry, I need to go back to where we stopped yesterday. That is where we stopped yesterday. We looked at a simple example, actually the simplest example probably. So it's the two-loop bubble with massless propagators, which defines a family of integrals with two propagators, which when the exponents, I call it nu1 and nu2. Of course, it's symmetric in nu1 and nu2. And we said, okay, in the end, well, we also saw that integrals that do not depend on any scale, they always vanish. So from that, we concluded that the only thing that they need to consider is the case when both propagators are raised to positive powers. We derive the IBPs. Well, these recursion relations, they are often just called IBPs, which give me these recursions, which we can rearrange as ways of always. So if at least one of the news is not equal to 1, then I can always replace an integral by a linear combination of two other integrals where one of the two exponents is lowered by 1 unit. And we represented this on a lattice. We only need to consider the first quadrant because everything else is 0, it's scalars. There's the symmetry between, along the diagonal in nu1 and nu2. And we said if you start from a point on this first quadrant, you can replace it by two other integrals where you have lowered one of the two exponents, and you keep going recursively until you reach the lower left corner, which is the point 1, 1. And so you see that every integral in the first quadrant is in the end just going to be proportional to the integral with exponents 1, 1, which is the bubble with unit powers of the propagators. Okay, and that integral, well, you've probably all computed it in your quantum field theory class. The integral expression is shown here. The integral expression is not so important here for the discussion. Okay. Now, any questions about this? This was the recap of what we did yesterday. Okay. So what we've done here is we got these recursions and we've solved them, right? So we've drawn this lattice and we saw how we can move in this lattice until we reach the point that we can no longer reduce any further using our recursion. And we called it a mass integral. Now, in practice, your integral will not just have two propagators, so two exponents. It may have 4, 5, 6, 10, maybe more. So this idea of drawing this lattice and moving around in this lattice and seeing how you can solve the recursion is not gonna help you. Well, it's just gonna be too complicated. So solving the recursion can be very tough. Now in practice, one does something different. What you do is, well, the recursions, these IVPs, they are linear, right? But that's clear. Now, you have this whole lattice of integrals, this whole family of integrals. Of course, in every concrete calculation, the exponents that you will get are very constrained. You will not get the propagator raised to the power 1000. You will get it raised to the power 1, to the power 2 maybe, and that's pretty much it. So you don't care too much what happens for very large values of these exponents. So you may just as well say, okay, let me restrict to the values of the exponents. For example, let me restrict them, well, let me restrict the sum of them to treat them all on the same footing to be less than a certain value. Okay, if you think in terms of the lattice, it would be like you draw, well, you just consider a box and you just consider the point on the lattice that lie inside this box. Now, if you consider this box, I hope it's clear what I mean by this. It means like doing something like this. So I would say that I only consider values of these exponents that lie inside this box. Okay. And I do that because I know that those are the only things that will show up in my calculation. If you do that, you have a finite number of points, and you have these linear recursions, which will give you a linear system, a finite dimensional linear system. So in the end, you can translate solving these recursions for all the points that lie inside this box to solving a very large linear system. And you do the same by Gauss elimination. And that is what people do in practice. So in practice, you essentially, you decide on if you want such a box, and you write down all the linear relations that you have for the points inside this box, and you solve them, which I guess you can see from this example. If I draw such a box here, and I generate the linear relations among the points in that box, and I do it explicitly. I plug in the values of what the news are for this point, for this point, for this point, and so on. In the end, I will end up writing every integral inside of this box as just being proportional to this integral here. So I have achieved the same thing without having to figure out how to solve the recursion in an abstract way. Okay, solving the recursion means that you have to find these ways of lowering the exponents. Here, I just get a linear system and I solve it. Now, this is what people do in practice, and there are, just want to mention, there are computer codes that have this implemented. So there are public codes that implement what is called the Laporte algorithm. Never mind what it is. It's just an efficient way of generating this large linear system and solving it in a smart way. And there are various public codes which are called here. There's one called air, one called fire. There's another private one called water. And then Lighthread, Kira, they use that, a whole collection of them. They all have their strengths and their weaknesses. But this is just to tell you that if you do this in practice, you don't do it by hand the way we did it now in the case of the two-point function, which was more like a pedagogical example. But you would use one of these codes, and you would just give it the integral. Like in our case, it was like the integral 7,4, and it would give you its decomposition into the basis down here. So all this is automated. That is very good. I should also ever say that right now, this is one of the bottlenecks, because these linear systems that you need to solve can be gigantic. It can be millions or billions of equations. And they're not just linear systems with numbers, but they're linear systems with like symbolic inputs. The coefficients of the system are themselves functions of the kinematics. And you quickly run into situations where the memory on your computer is not large enough anymore to just store the system.
I have a question.
Yeah.
Are you always guaranteed that there's a solution, determinants being non-zero or whatever?
Well, the system is indeed under constraint, because you know that you want to find a basis for the solution space. So the determinant of the system is 0 because you cannot solve it. And you can only, no, sorry, it's,
I see.
I mean, you have things that you cannot solve for, right? That's the base of the solution space that you're looking for.
Right.
What is guaranteed is that this basis exists and it's finite and non-zero. And the number of elements in that basis is non-zero. That is proven mathematically.
Okay.
Where you do make, in principle, a leap of faith is that when you construct this box here, that the box in some sense contains the basis. There, technically, you make a leap of faith. Of course, in practice, you know that the basis elements will be the things that have exponents 1 or 2. So if you make new marks large enough, it won't be an issue. Okay? Good. So let's look at another example, which is a bit more complicated than the bubble that we looked at. And also we will look at it. We'll not go through it in detail. We'll just discuss it. Also because we will use this as the example in the rest of the lecture for other things. So the example is the one loop 4-point function. Completely massless. So all propagators have 0 masses. Okay, so all lines are massless, and also the external legs are all massless. Let's just simplify the discussion. Momentum is conserved, and I do it in 4 dimensions, -2 epsilon. I do dimensional organization. And I have 4 exponents because there are 4 propagators. The news are integers. And so now I have a 4-dimensional lattice. So this is already something I can no longer visualize because I would need 4 dimensions. So I can work out what the IBPs are. Sorry. Before we get there, just this will be useful later on. This integral here, well, it depends on the external. So what does the integral depend on? Independently of which exponents of the propagators I pick. So what are the Lorentz invariants I can form out of my external momentum? Well, I have 4 external momenta constrained by momentum conservation, so I have 3. They all square to 0. So the only invariants that matter are the ones, well, between 1 and 2, 2 and 3, and 1 and 3, which are the conventional things that you call ST and U, usually 1 and 3. And you know that ST and U are not independent, but they are related by S plus T plus U equals 0. Okay, this is something you probably know from quantum field theory. We will come back to that. This we'll read a bit later, but this is probably something you know, that the massless 4-point function depends on essentially S and T. Well, at one loop. So now I have this family of 4-point functions labeled by the exponents, nu. And I can ask, okay, what is the minimal set of integrals that I need? What is the basis? What are the master integrals? MI stands for master integral. And, well, you can feed it one of these codes, and it will tell you that each of these integrals, depending on what the news are, is a linear combination of 3 integrals only. So one will be the massless 4-point function when all propagators have exponent 1. So that is the box as we know and love it. And then you need 2 2-point functions. One where the new 2 and u4 are equal to 0, and 1 when u1 and u3 are equal to 0. This corresponds to two bubbles that I get from either removing these two propagators, then I get this. So if I remove these two, and I keep these two, I get this. While otherwise I get this. Okay, so it depends on which propagators I remove. Because if I put an exponent to 0, the propagator is not there. So it's like pinching the edge. And those are bubble integrals, precisely the bubble integrals that we've discussed already. So in some sense, the only integral that I get is this one here. So you see that in order to evaluate all possible one-loop 4-point functions, completely massless, I need these two bubble integrals that we know, and I need this massless 4-point function. That's it. That's enough to compute every integral in this family. And since we know the bubble already, we just need this additional box. Note in particular, there's no 3-point function that survived. That is an accident. That is an accident because I consider it completely massless. If you add masses, then you would also get 3-point functions. Okay. So that's just another example of how these recursions work. And you can use this in principle to find the basis of integrals for every possible family of Feynman integrals, where the family is defined by the graph, the set of propagators that you consider, and the element in the family are the exponents. Now comes the other question: how do you compute? Once you find the basis, once you find the master integrals, how do you compute them? And this is going to be the next topic. But before I go there, I think this is a good time to take questions.
Sorry, I have a question. Can you go back one slide, please?
Mm-hmm.
So you started with a phi-cube interaction with a phi-cube theory, right? Or not?
No, I just considered an integral that is made out of propagators.
Ah, okay, I see.
Oh, yeah, okay, maybe that is a very good point. Yeah, maybe that is indeed a very good point. So when you compute these integrals, you always forget about the physical theory. These are mathematical objects. Mm-hmm. So the integrals that you get may correspond to graphs that have nothing to do with the theory that you're looking at. Mm-hmm. For example, just to give you an example, yeah, maybe that's a very good point. Imagine you are in QED, just to consider a concrete example, okay?
Right.
So, and let's do something like this. I have this graph here. That's a QED graph, okay? Mm-hmm. Now, what is the integral that you want to consider? The integral that you want to consider is actually this.
Mm-hmm.
Okay, because the red wavy lines have nothing to do with the integral.
Right, yeah.
So you would now say, but well, what does that mean? This is now a 4-point interaction between fermions, which has not, because all the black lines were fermions, right?
Right, yeah.
You would say, but this is now something that comes from 4 fermion interactions, which have nothing to do with QED.
Yeah.
But it's immaterial, okay? The integral is just defined by the propagators that you have.
I see. Nice.
And maybe let me just dwell on this for a second because it's very important. Let me consider the following graph in QED. Mm-hmm. It's a 2-loop graph, right? Mm-hmm. Now, for me, this would actually be, well, apart from the fact that it is actually, okay, let's just say it. Yeah, it's a bit trivial. Let me do a slightly more complicated example. Because this one is just a product of 2 integrals.
Yeah.
So let me look at something slightly more complicated. Let me look at the following graph, which you would get in QED. So this would be a QED graph, right?
Right.
Black lines are fermions, red wavy lines are photons.
Yeah. Mm-hmm.
And clearly this is a three-loop graph, right?
Right.
And well, you see, so how should I say it? The way you would actually look at this graph is different. The way you would look at it is, let me use blue lines to indicate that I forget about fermions or photons.
Mm-hmm.
I would look at it as follows. Because you see, each of these lines is exactly the same propagator.
Mm-hmm. Yeah.
So it is like this line having nu equal 3.
Right. Okay, I understand. Yeah. I see.
Okay?
Mm-hmm.
And this graph, the blue graph, clearly has nothing to do with the theory that you're considering, right?
Mm-hmm.
This has weird kinds of interactions like this. Like this is a 4, it would again be some 4 Fermi interaction. If you
Yeah.
And even weird propagators that have higher powers. So it's definitely not a graph that you find in your theory, but that is the integral that you want to compute. Because that is the one where you have massage. It's such that the propagators appear in some, well, we have identified the mathematical structure. Here it's just that you split these propagators out, but it's a material. I can just say that this is the same as this thing cubed.
Mm-hmm. Yeah, I understand. Yeah. Thanks.
Yeah, thanks. This was very good comment. So you should not think as these things as coming from theory. They really are mathematical objects, and it's in some sense that is part of what, well, the people that do computations the way they think, and that's maybe why I didn't insist on it, that these graphs and these integrals are just purely mathematical quantities. You forget about the physical origin. You manipulate them as mathematical quantities. More questions? Okay. So then let's come to the question of how you actually evaluate these integrals, which is a whole business on its own. And there are many techniques how you can do this. Many. Here I'm going to discuss one, and maybe we'll mention other techniques later. I'm going to discuss one because that's probably the one that has had most of the impact. But it's not the only one. And depending on what you want to do, maybe other techniques are there. And the idea is the following. So we have seen that differentiating with respect to a loop momentum, and I remind you that in my convention for the lecture, K are always loop momenta, P means external momentum. So we have seen that if I differentiate with respect to a loop momentum, then via integration by parts, this is the same as shifting the exponents. So differentiation means shifting the exponents. But so far, we've only done it for the loop momenta. Of course, when you look at it, so the basic formula was here in blue. I mean, you see that this equation here, the fact that differentiating amounts to shifting news doesn't care about differentiating with respect to K or differentiating with respect to P. So differentiating with respect to external momentum will have the same effect. So I could just as well differentiate with respect to an external momentum. And this would amount to shifting the exponents as well. But the trick is now that if you differentiate, if you start from a basis element, you differentiate with respect to external momentum, the result will be a linear combination of integrals with shifted news. These objects that appear in this linear combination will not be basis elements because the exponents have been shifted. But from what we just discussed, you know how to write any point on your lattice. So for every value of the exponents, back in terms of the basis elements. So if you differentiate with respect to an external momentum, you produce a linear combination of objects with shifted exponents, which are not basis elements, which you can write back in terms of the basis elements. And that's the general strategy. So in other words, you can always get a system of differential equations for the basis elements, for the master integrals. And that is at the heart of this whole idea, namely that Feynman integrals will always satisfy differential equations in essentially the external kinematic data. Okay, is the general idea clear? So that's the general idea. Now, of course, as usual with these things, things are not so easy. The problem is that, you see, these differential operators that I considered here, which are the ones that shift in use, are the ones with respect to the four vectors. Why? Because my integrand, the objects that appear in the integrand, are the p's, the four vectors. So I should differentiate with respect to four vectors. But the integral, after I've done the integral, by Lorentz invariance will depend on scalar products and not individual p's. So actually, the function that I get, that I want to compute the derivative of, is a function of Lorentz invariance dot products, while when I put the derivative into the integrand, it acts on things which depend on four vectors. On top of that, if you think in terms of the box, there was this constraint, s plus t plus u equals 0. So not all of these dot products are independent. So there are these computing derivatives with constraints. Right? Because this constraint tells you that the derivatives with respect to, for example, S12, S13, and S23 cannot be all be independent. So we will go through this in detail now for the example of the box 1, 1, 1, 1. Remember, that was the only master integral for the 1 to 4 point function that we don't know yet. And we'll see how we can evaluate it with differential equations. And if you remember from what we said yesterday, we said that, well, actually, if you have, well, the box, maybe let's go here. The box is a function of 4 momenta. And then P4 is the sum of the others by momentum conservation. But actually, by Lorentz invariance, it will be a function of 3 dot products. Sij is Pi dot Pj. But actually, since S12 plus S23 plus S13 is equal to 0, it's actually only a function of f, s, and t. And we said yesterday, if you have a function which depends on a certain number of scales, by dimensional analysis, you can always pull out one scale. And then the rest is a function of ratios. So x here is t divided by s. So I just want to show you that there are different ways of thinking about it. In the end, the only thing that you care about is this I of x. That's the only non-trivial function that you need to compute. But in order to compute the derivatives and to shift the exponents, the differential operators that you have at your disposal are things of the type d over dpi mu, Well, the things that you want to compute in the end is d over dx I of x. So these guys act clearly on this function, which depends on P1, P2, P3. But what you want is this. Okay, and you see there are several layers in between, and it's a bit subtle. That's why I want to go through it. In the end, it's just chain rule. You just have to do changes of variables properly, but with constraints, and that's why it is a bit subtle. Is the general strategy clear? Okay. So how can you get this differential equation, this d over dx of I of x? We had in the previous slide. Well, so we said the things that you can, that you know how to evaluate and shift the exponents are these d over dp mu. Now, these are derivatives with respect to 4 vectors. Since you're looking at Lorentz invariant quantities, better contracted with something, some other 4 vectors, some other external momentum, and then you get Lorentz invariant operators, which are called here Dij. If you look at the box integral that we took as an example, those are the only operators that you have. If you have massive propagators, I could also differentiate with respect to the mass in the propagator. But we're looking at the massless integral as an example, so we're not going to discuss this. But you can easily convince yourself that also differentiating with respect to the mass in the propagator will have as a result just shift the exponent of the propagator. Now these differential operators, Dij and also the derivative with respect to the propagator mass, they are Lorentz invariant differential operators. And they naturally act on the integrand. I think that's the important thing here. So they naturally act on the things in the integrand, because integrand is a function of 4 vectors. So for example, let's take the box as an example. You can easily check, I leave it to you as an exercise, that if you act with the operator d33, so d33 would be p3 mu, dp3 mu. If you act on it with it on the integrand, with the box, and use the definitions that we gave, well, maybe, yeah, just let's maybe quickly go back to the definition of the box that we gave, which is here. So if I differentiate with respect to P3, you see that the only propagators that depends on P3 is D4, because P4 is minus P1, minus P2, minus P3. The others do not depend on it. So you only differentiate in the end the propagator 4. Everything else is just a spectator. D1, D2, D3 are spectators. So that's what you see here. So if you only you differentiate propagator 4, which now become squared. And then you have the derivative of, well, what the inverse propagator, which now appears in the numerator. And now I remind you that actually 2 times k p3, I can write it again as k plus p1 plus p2 plus p3 squared plus other terms. So this would again be d4. And so you can actually show that this integral that I produce in the integrand is equal to a sum of 2 integrals, this and that. The one in gray is the integral I started from, the one with unit powers per propagator. That's a master integral. The pink one is clearly not, because my master integrals were the 2 bubbles, which are the integrals 1, 0, 1, 0, and the integral 0, 1, 0, 1, and the 1, 1, 1, 1. This is the integral 1, 1, 0, 2, which is not one of our basis integrals, but I can write this linear combination of basis integrals, and I get the following result. So now you see, and what I've done is I've written the derivative of this master integral, the 4-point function, as the 4-point function itself and a bubble integral. Okay. The bubble integral I know, so I have now obtained the first order linear differential equation for box 1, 1, 1, 1. I remind you that this is actually a bubble. So that's a simpler integral. Now, this is the integral, the differential equation with the differential operator P3 mu dP3 mu. Yeah, so, okay. So that is the differential equation. One thing, well, let me just mention it. We can go through it in more detail if you like. These differential operators here, this and that, they are also not all independent. In particular, you can show that the following relation always holds. So this thing here is what I called DII. If you sum all the DIIs and you sum all the derivatives with respect to the mass, you get back the integral itself times the number, which is just the energy dimension of the integral. So there's a linear combination of integrals at X trivial. If you want the discussion sessions afternoon, we can also discuss where this relation comes from. It's literally just, well, this combination of differential operators is literally the infinitesimal generator that would rescale every dimensional quantity. And if you rescale every dimensional quantity, well, you produce the dimension of the integral. The eigenvalue of that operator is the dimension of the integral. We can, if you want, we can go through the derivation. So why do I mention this? Well, just to say that A, these operators are not all independent. B, this is an important check, because if you compute all these differential operators, you know that they cannot all be independent, because the dimension of the integral you know, so you can use this as a check of the calculation. Okay. So next step is to say, okay, I have now know how to compute all of these, the action of all of the operators Dij. But actually, we know that the box is a function of Lorentz invariance, S12, S23, S13. So actually, what I would like to compute is the action of the operators Sij, right? The derivative with respect to Sij. That is easy, because I can just use the chain rule. For example, you can easily check that D12, which is, remind you, D12 is P1 mu d over d P2 mu. This operator, well, you just use the chain rule, and you write it as, well, ds12, dds12, ds13, dds13, ds23, dds23. And of course, you can easily see that yeah. So, well, you can easily check that this relation holds. So clearly, when you look at here, S13, which is P1 or P3, differentiate with respect to P2, this is 0. If you look at this, S12, differentiate with respect to P2, so this will be proportional to P1 mu. But you have to contract it with P1 mu, so you get P1 square, which is 0. So also this term goes away. And so you're just left with the last one. This is proportional to P3 mu. Contracted with the P1. So you get S13 times DD S23. So it's just chain rule. It's nothing magical. And you can do this for every operator Dij and write every operator Dij. They're all Lorentz invariant in terms of the Lorentz invariant operators differentiate with respect to the dot products. And you can invert these relations and you get relations like these. It's not particularly difficult. I leave it to you as an exercise that the operator, well, this D down here is actually this combination here. I should have said that. This is D. Yeah, D equaling on I. Ah, why did it say this? Okay. That this operator, this combination that acts trivially, is now the following. I leave it as an exercise.
Sorry, that's true just for the massless case or for the both cases? Also for the massless?
Actually, what is equal to this will be this piece, okay?
Okay.
So for the box, this is anyhow absent.
Yeah.
And the piece that depends on the momenta for the box, for this massless box, reduces to this. Because these relations here are just valid for the massless box, because if I have more complicated kinematics, I would have more than just S12, S23, and S13.
Yeah, okay.
Okay, so I think this is a good time to take a short break. We can take, yeah, let's restart at 11. I can take a cup of coffee, and after that we go to the, well, the non-trivial piece, which is understanding how to compute derivatives. So this was trivial, this was easy. And now comes the problem, what do you do with the fact that actually we have now three differential operators, derivative with respect to S12, derivative with respect to S23, derivative with respect to S13. But you also know that these three invariants are not independent, because S12 plus S23 plus S13 is equal to 0. So your operators, as we've written them, cannot be correct, because I cannot change the value of S13 while keeping S12 and S23 fixed. Doesn't work, because they must sum up to 0. And that's what partial derivatives would do. You would change one variable, keeping the others fixed, but I cannot do that. Okay, so it must be a little bit more subtle than what we've done so far. I think before we go there, let's first gain some energy and get a coffee, unless there are questions. Okay, so don't see any questions, then let's reconvene in 10 minutes. Good. Okay, so then let's continue with our discussion of how to compute Feynman integrals from differential equations. Right, the first step was to see how we get the differential equation, then we do that on the example of the massless box. So share the screen. Good, so that's where we left. And so we started from these differential operators Dij, which are Pi mu dd Pj mu, which are Lorentz invariant. So the first step is to transform them into these operators here, just via the chain rule, and this gives me these relations. Now, the next step is that I know that S12 plus S13 plus S23 is equal to 0, which means that dd S12, dd S13, dd S23 cannot be independent. So I somehow need to fold that in, because as I said, partial derivatives would mean that, for example, I change S to 3, keeping the other two fixed, but then the constraints tells me that I cannot do that. So in principle, what I'm saying is not something particularly deep. It's just a thing in principle, well known. It's what one learns in calculus in first semester, but it often leads to confusion. So for me, the cleanest way is to proceed as follows. I have, well, let's go back just to remind us of the notation. So I want to compute this box, which depends on 3 Lorentz momenta, 3-4 momenta. It's a Lorentz invariant function, so it only depends on, it's a function which I call B, which depends on the dot products between the 4 momenta. But now I also know that the S plus T plus U is equal to 0. So actually this U, this is a U, of course. This function of S, T, and U is only a function of S and T, which I call F. And, well, clearly it must be equal to this function B, evaluated S, T, and U, but U being constrained to be minus S minus T. Okay, and that's one way to parameterize it. And now what I want to do is I want to compute the derivatives of this function S with respect to S and T. For example, and I just, again, I use chain rule. So DDS, when it acts on F, well, F is the same as B. And now comes a step which, it sounds innocent, it looks innocent, but it's actually, when you think about it, it's a bit weird. Because actually, when you see, when DDS acts on B, it acts in 2 places. It acts here, but that is where S12 lives. But it also acts here, which is the derivative with respect to S13 with a minus sign, which comes from the fact that you have minus S in there. And in the same way, I can compute the derivative with respect to T. Now I need to act here in the second slot. And again, in the third slot with a minus sign, because I have a minus sign. So it's actually pretty easy, but it leads to some weird looking formulas, which are actually obvious. So for example, S was defined as being S12, T is S23. DDS is not DDS12 because of the constraint, but it is DS12 minus DS13. Okay, that's why I want to go through this in detail. Just because S is equal to S12 doesn't mean that differential. When I say S12, I mean P1 dot P2. Just because S is P1 dot P2 does not mean that the derivative with respect to S is the derivative with respect to P1 dot P2, because I have additional constraints among the kinematic variables. It's obvious, but many times people get confused. And then down here, this is just, again, this quantity that acts trivially. You can check that this guy here, when you plug in the relations to DDS and DDT that we found, you get this relation down here. And finally, we said, well, what you care about is only the derivative with respect to x, which is t divided by s, because the other dependence is trivial. And again, I will be overly pedantic because I want to make a point. So yeah, let me be overly pedantic. So my function f, which depends on s and t, we said I can pull out s, dimensional quantity, and then I just have this function I, which depends on x. And let me actually pull out a quantity, what I call sigma, which is equal to minus s. The minus is a bit immaterial for discussion, it's conventional. But essentially, let me introduce the new variable sigma, which is equal to s, up to a sign. And the reason for doing that is because I want to highlight that what we're actually doing here is doing a change of variable from S and T to sigma and X. In order to get things right, you have to think of it in that way and do the chain rule really from ST to sigma X. Why do I insist on that? Because when you look at it, well, let's do the chain rule. dd sigma is clearly ds dds, dt ddt. And you just use the formulas given above. So you know that here ds by dx is clearly 0 because s doesn't depend on x, while dt dx, if you compare with what is up here, gives you minus sigma. So that's clear. So you get that ddx is actually the derivative with respect to t multiplied by sigma. Okay. So why was I so pedantic about sigma and x and s and t? Well, let's look at what the derivative with respect to sigma is. Well, clearly, again, ds dds, dt dt. And well, what is ds d sigma? Well, that is clearly -1. And what is dt d sigma? Well, that is minus x. Sorry, use blue again. That is minus x. So you get to the strange thing that s is equal to sigma, but dds is not dt sigma. Again, it's obvious if you do it properly, but I want to insist you have to do the changes of variables properly and consistently. As soon as you always have to do it properly, otherwise you just run into problems. And people always get confused when they work with Feynman integrals because they say, the thing that I've pulled out is s, so dds must be, well, dd sigma is dds. It's not. There's this other term. Again, if you look what this trivial operator is, that, well, this linear combination of differential operators like trivially that we call d, it's this guy. And now I see there's just a derivative with respect to sigma. And does it act trivially? Yes, because dependence on sigma is completely trivial. And that's not a way to see that dd sigma is not dds. dd sigma is d, roughly speaking, from here. But d involves both s and t. Okay, this is trivial, but I want to point it out because people always get confused. So the upshot is that in the end, if you now go backwards, we have a way. So our box integral that we want to compute is the sigma -2 minus epsilon times this function I of x. What I want to compute is d over dx acting on I of x. And if you now unfold what we've been doing is we've managed to write ddx as a linear combination of dds and ddt, actually only ddt in this case. These were linear combinations of these operators here. And those were linear combinations of the dij's. And the dij's, when they act on the integrands, they shift the u's. So what you get from that is you get that you can compute the derivative of I of x, or of the box, with respect to x, which is the only variable that actually matters, and write as a linear combination of master integrals. Well, again, it's a linear combination of master integrals, so you get a differential equation in x for the box integral. You just have to do all the changes of variables consistently. Okay. Are there any questions about this? This was very explicit, but I thought it would be good to go through it to show all the details of how you can get the differential equations. We will look at the differential equations with the box in a second. No questions? Good. So another way of saying this is as follows. Let me introduce a vector I, which is this vector here. So it's the vector of all my master integrals. So there would be the master integrals we had was this one, and this one. So let me package them in a vector. What we've managed to do is we've managed to compute ddx of this vector I, so of each master integral. And the derivative of a master integral is again a master integral, a linear combination of master integrals. So the derivative of I will be, well, will involve I itself, multiplied by a matrix. So that will be the general form of the differential equation that you get. So if you package your master integrals into a vector, then you get a linear first order differential equation for the vector of master integrals. Now, if you have, here it was particularly easy because the only variable that actually matters is x, is the ratio of T over S. In general, you can have more degrees of freedom. So let me call them generically xi. In the example of the box, it was just x, which would be x1. And so, of course, then I can compute the derivative for each with respect to each of these xi's. And for each of these xi's, I would get the differential equation. So I could now go and generalize this here to xi. And let me call this matrix here AI. So there's a matrix AI. And in order to keep the notation a bit more compact, it is useful to introduce the language of differential forms. So I'm not sure if everybody is familiar with differential forms, but we can also go through it in the discussion section in the afternoon. But in the end, what I'm looking for is objects of the type, well, let's say F, Fi, of x1 to xk, dxi. So they are total differentials. And the total differential d is this operator here. So it's essentially a way of packaging things for now. So instead of writing this, I would write it as di is equal to some matrix A times I, where this matrix A here would be this. If you don't know what differential forms are, think of it as these dxi's as a way of just writing things in a compact way. The only thing you need to know for now about these objects is that the x objects, dx1, there's a way to multiply them. It's called the wedge product. It's called the wedge product. Roughly speaking, it's just multiplying these objects, but the multiplication is antisymmetric. And since the multiplication is antisymmetric, you get that if you take the total differential twice, you must get 0. Why? Well, because this would be dxi, which dxj, d squared, dxi, dxj. So f, and clearly this is symmetric, and this is antisymmetric. So it must be 0. Okay, so the total differential square of an object is always 0. And if you take a function f and you compute its differential, df, that is what is called the differential one form. So this object here, well, a linear combination of objects of this type is called the differential one form. That's all you need to know about it. Just to follow the lecture, it's just vocabulary. Those who know what is behind it mathematically know that what it means, but just to follow the lectures is enough. We can go, for those of you who don't know what this is, we can look at it more in more detail this afternoon in the discussion session. Okay. So,
sorry, what is the range of this small I? Because you had sigma and x before, right? But now, so
here I'm just talking about variables. Okay, could be anything. It's the number of degrees of freedom. So if you go here, and the axis you have here, if you go to the box, you could say, well, it's just x because that's the only non-trivial object that I have. You can also say x1 is x, x2 is sigma, and then you include also dd sigma, but the action of dd sigma is trivial.
I see. Okay.
Okay, so this is just to say that this idea of using a total differential and these dx objects, it's just a convenient way of packaging things for now. Okay. So in the end, you see the information is all in this differential, in this matrix. And this matrix will depend on all my degrees of freedom, all my xi's. So in terms of, for the box, it would be x or x and sigma if you want to drag along the information on sigma. Many times what people do is, for the box, for example, they would put sigma to 1 because the dependence on sigma is so trivial that you don't care about it. You put it to 1 and you just look at it as a function of x. So your matrix A will depend on all your degrees of freedom, xi, but also on epsilon, the dimensional realization parameter. Okay. Now, what do you know about this matrix A? So what are they? Well, remember how A is obtained. So let's go back to the box. So A is obtained by this chain of changes of variables. In the end, it boils down to computing these operators here. And then, well, you shift exponents and you bring it back to the basis. But you see, since you only ever manipulate the integrand, which is a rational function, and the only thing you ever do is differentiating the integrand, which is a rational function, the only things that you will ever produce are rational functions in the dimension d, or the dimensional realization parameter epsilon, and the kinematic variables. So by construction, the matrix that you will get from this procedure will be a matrix of rational functions in both epsilon and x. So the matrix is rational. It's rational functions in your kinematic variables any dimension regularization parameter. Always. That's just by construction. So what else can I say about this matrix? Well, is the matrix somehow constrained? Let's just look at point 2, what is called integrability condition. So we said that the square of a total derivative is always 0. But now I can go and say, well, I can, if I do d square I, well, this is like d of di, but di is a times I. And now I use the Leibniz rule. So I act with the derivative on a or on I. And if you do it properly, the Leibniz rule here is a minus sign. This has to do with the fact that it's antisymmetric and you need to jump, well, you need to reorder terms and therefore you get something antisymmetric. You get a minus sign. But di here is again a times I. So this means that I must always, this matrix must always satisfy the following identity. That this must be equal to 0. For every vector I, it doesn't matter what it is, because whatever my vector I is, d square I must be 0. So the only way that that can happen is if that A satisfies this condition. So you see that actually A in some sense satisfies the differential equation itself. Okay. Now, those of you who are, well, I guess you're all a bit familiar with gauge theories. This quantity here is actually very reminiscent of F mu in QCD. If you write this thing, this would be something like d mu a minus d nu a mu a plus, let's forget about the sign conventions, plus I minus I. Let's forget about the coupling constant. It would be something like this, huh? Now, this is actually the same as this. The derivative is this. And A here is a matrix, I remember. So A would be A mu, if you want this. It's like this. Well, rather, sorry, let's put it like this. Let's write it like this. So this would be your A quantum field theory. It's a matrix of differential one forms. dA would be precisely this, well, the kinetic term, if you want. Well, here you have the quadratic term, which is antisymmetric into A's, which is precisely this term. So what you actually get is that this integrability condition, that A satisfies the differential equation itself, you can interpret it as, if you want, gauge theory. In the end, that's what it is, where A is the gauge field and the curvature is 0. The field strength is 0. This analogy will help us to explain many of the formulas that come now, because all the formulas that we get now for these differential equations are essentially formulas that you know from gauge theory. In particular, what would be a gauge transformation? Well, a gauge transformation would be that you say, I have a vector of master integrals I. Well, it's a vector for which I write down the differential equation. But I could do a rotation. I could choose another vector of master integrals. Right? I could choose a different basis on my lattice. Now, two bases are related by some matrix, by some rotation. This rotation will, again, depend on all the variables in the problem. So if I satisfies the differential equation, what is the differential equation satisfied by J? It must be a different one. So what is the matrix A, but if I use the basis J? Well, you can easily check it. You start from di, which must be 0. If I satisfies the differential equation, so that must be 0, because I satisfies the differential equation. Well, but I is equal to m times j. Sorry. Yeah, I is equal to m times j, and the derivative of I introduces an a. But I is m times j, so I can again use the Leibniz rule when I act to compute the derivative of m and the derivative of j. And that probably here I made somewhere a sign mistake. Because this sign should be the same as this one. I'm sorry for that. And now what you get is you get that J satisfies, and you just solve for dj. You get that dj satisfies a differential equation with the matrix A prime, which is related to A via this relation, which you can easily identify as being, well, it looks very similar to the way you're in quantum field theory, the gauge field will transform if you do gauge transformation. So change of bases are gauge transformations. Integrability, the fact that the matrix A is constrained, would be the fact that the curvature is flat. Yeah, so that gives you, it's just a language that we will use. Okay, so you can think of these differential equations that you get as having all the properties that you know from gauge theory and quantum field theory. Yet I have not told you how to solve it. So how do you solve it? And this can be very, very tough. So in general, it's extremely hard to solve these equations. However, here we have to remember that if we work in dimensional organizations, we don't care about the dependence on epsilon so much. The only thing that we care about is that these objects define expansions around, say, 4 dimensions where epsilon is equal to 0, and I just need the first few terms in this expansion. And that is easier to get. So even though I may not know how to solve these differential equations exactly in dimensional organization, I may know how to extract what I need, which is just the first few terms in the expansion around 4 dimensions. And to understand that, well, let's use this analogy with the gauge transformations. So we said that these matrices that I get from differential equations, they depend on all the kinematic degrees of freedom and on dimensional organization parameter. And assume that there is a gauge transformation, so just a rotation, such that the dependence on epsilon becomes trivial. It just factors out with a linear factor. Assume that such a gauge transformation exists. Assume that there's a gauge where the gauge field has this special form. Okay. Here I know how. Sorry. So assume that there's a gauge transformation. So there's a new basis J, which is related to I by a rotation matrix M, and the new gauge field, the new matrix A, is given by this form, such that it takes this special form where epsilon factors out. Then, of course, the new basis vector J, well, the new vector of mass integrals J, will satisfy this differential equation in this green box, where the dependence on epsilon is factored out. Okay, so what have I gained? Well, the dependence on epsilon is trivial, but what does it actually gain? What do I actually gain? To understand that, let's use again the analogy with gauge theories. So how do I solve this differential equation? Well, what I write down, this general solution, I can always write it as the path-ordered exponential of the gauge field integrated between 2 points, acting on a vector of initial conditions. We will define, we'll go slowly because this is important. So what has happened here? Imagine I give you the value of the object I want to compute at some point x0, which is my initial condition. And I want to know what does the solution look like at the point x. And I have a differential equation, which is dj epsilon a x j. Or I can even write, if you want to have it a bit more gauge theory, there's a covariant derivative acting on j equals 0. Okay, so I know the solution down here at this point x0. I want to know it at the point x. Well, what do I need to do? Well, I know in a gauge theory how to transport information, which is using Wilson lines. So let me choose a path that goes from x0 to x. And let me parallel transport the solution that I know down here. Also depends on x and epsilon. Let me use parallel transport to bring it to the point x. Parallel transport is it's Wilson line. So what is the parallel transport operator? Transport. Well, we know what a Wilson line is. That is the path-ordered exponential of the integral along the path of the gauge field. But the gauge field is this, right? Epsilon times a of x. And so the result of this parallel transport will be my parallel transport operator, which is this path-ordered exponential, acting on the initial condition. And what was the integrability condition? So the integrability condition was that I need to satisfy dA. I think I made a sign mistake for the minus sign, should be something like this. This is equal to 0. This we said in gauge theory would be the field strength. So field strength is 0, curvature is 0, space is flat. And if space is flat, then parallel transport doesn't depend on the choice of paths, because I could also have chosen this path. Right? Could have chosen another path. And if the space is flat, if the curvature is 0, then the parallel transport doesn't depend on the choice of path. So the integrability condition, the fact that the space is flat, ensures that I can choose whatever path I like. Parallel transport is a Wilson line, it's a path-ordered exponential. And so I can transport the solution anywhere I like. And also note that the path-ordered exponential is a matrix, okay? This quantity is a matrix. It's the path-ordered exponential of the gauge field. Okay, so far I've just used this notion of parallel transport. What does it buy me that has said there is a gauge in which the matrix, but the gauge field has a special form. Well, remember that I only care about the first few coefficients around epsilon equals 0. And you see now that the only place where epsilon appears is in this exponent. So if I expand this exponential, this path-ordered exponential in epsilon, I can just truncate it trivially, because the expansion, well, the expansion is trivial. It's the exponential of epsilon times something. So let's do that. Let's take, for example, let's assume that my matrix A tilde, so I remind you that there was a gauge in which the new matrix, which are called A prime, looks like epsilon times A tilde. And for the sake of the example, let's say A tilde has the following form. It is some matrix A0 times dx over d over x. And there's a matrix A1 times dx over 1 plus x. Why this special form? Because that will be the form that comes out for the box integral. And so let's expand this exponential. So we have this path-ordered exponential, this parallel transport. At leading order in epsilon, clearly it is just 1. At the next order in epsilon, well, it's just the exponent, right? It's just epsilon times the integral of A tilde. But A tilde, I know what it is. So I can now plug in A0 and A1. At the next order in epsilon, there's epsilon squared. Well, here you have to take into account that it's a path-ordered exponential. So you have this ordering along the path where the first and the outermost integral goes from x0 to x. But the next one is ordered along the path. It just goes from x0 to t, where t is the integration variable that I had before. That's what path ordering means. It's literally what you know from Wilson lines in QCD. And so you can just spell out what all of these integrals are. So if I need to know the parallel transport operator, the path-ordered exponential, to second order in epsilon, which would be enough to compute my solution to that order in epsilon, I just need to compute these integrals. So you see that in order to solve my system, it's enough, okay, I have to give my initial condition, I have to give what the solution is at this point. That's the initial condition. And I need a parallel transport operator, which, if I find this gauge in which it has, the gauge field has a special form, I can easily expand in epsilon and truncate, and I just get these simple integrals to do. And the matrices A0 and A1, they are constants. I should have said that here. Up here, the matrices A0 and the matrix A1, they are constants. They do not depend on epsilon. Now, how to do these integrals, this we'll see later. I mean, you can easily see already here that this thing, for example, is just log x, for example, log x over x0. Well, we'll see that in more detail later. So here I just want to say that if you find a special form for the differential equation, then solving it using this parallel transport idea is very easy. The problem is, however, still that we started from saying, assume that this gauge exists, which in this gauge is sometimes called the canonical form for the differential equation. But does it exist? There's no reason a priori why it should exist. Still, there's a conjecture, which I think the first person who formulated it, maybe not concretely in this form, but implicitly was Johannes Sen, is saying that you can find a matrix M, could be gauge transformation, it's a rotation of your basis of mass integrals. This matrix is algebraic. The entries will be algebraic functions of x, such that in this new matrix, it's not quite what you want. You would end up with something where you have, well, the dependence on epsilon is linear. You see, it's slightly weaker than what we need. There's a slightly stronger version due to Roman Lie, but let's not go there. But the conjecture is that you can always find a way to change the basis for your differential equation by using a rotation matrix with algebraic functionless entries, such that the matrix has the form A1 plus epsilon times A2. The dependence on epsilon is linear. This is a highly non-trivial statement because if you start off with the differential equation, the dependence on epsilon can be as complicated as you like, essentially. Still, this matrix M is expected to exist. And in all known cases, we know it exists. And in some cases, even automate ways to find it. In many cases that are interesting, this A1 is 0. This is just an empirical thing, I would say. So conjecturally, you can always find a way to bring it to the form where it's linear in epsilon. And in many interesting cases, this A1 is 0. And then we have the form that we want. Namely, that it's just epsilon times something else. Now, when I say in many cases, in many interesting cases, we'll see that a bit more detail tomorrow. I just want to say here that there are all these steps are automated, or not completely automated, but there are codes that you can use to find this matrix A2, which is A1 plus epsilon A2. If A1 is 0, you have ways to find A2. If A1 is not 0, it's a different story. And we'll get back to that probably on Friday. That is if A1 is not 0, then you're getting to the frontier of what people can do. The case where A1 is 0 is the case that is by now well understood. Okay. Yeah, I think this is enough for today. It's time is up. We'll continue from here tomorrow. Are there any questions?
Yes, one quick question. So in gauge theory, x is a continuous variable, right? But
yeah.
now here x is discrete, right?
No,
so
x is continuous. X would be, the x here is, so x is a vector, right? Which has entries, and entries are continuous. They are.
Oh, okay, yeah. It's the Mandelstam invariance, right?
Exactly, yeah.
Okay, yeah, I see. So one more question is about, could you go to the slide where you write down this matrix notation for A and X, please?
Where?
You wrote down Xi times AI or something like that.
Yeah.
I think it's one more back, maybe.
Or you mean this?
Oh, no. Okay. Yeah, that one. So there I can see, I mean, you wrote down there that A is basically the sum of DXi times AI, right?
Yeah.
So my question is, okay, we know that A has the size of the dimension of the master integrals, right?
Yes.
So how do you know that that dimension is the same that dimension of the vector xi?
Oh, it doesn't. I mean,
but you are summing over I, right?
Yeah, well, but look at it. This here you have two AIs, A0 and A1, but only one X. So this would be the shape, this we'll see tomorrow, that you get for the box. So here, the I would be this.
Mm-hmm.
So A tilde will be a 3 by 3 matrix.
Okay.
Each entry in here will be of the type some number times dx over x plus some other number dx over 1 plus x. Or I can write this then also as A naught, as this form.
Okay, okay.
The number of variables is one thing. I mean, it's like in gauge theory, right? The size of the matrix, for example, for QCD is 3 because number of colors is 3. The X would be if you want the space-time coordinates. But
okay. Right. Okay. Now I
the
understand.
number of masters is like the number of colors you would have in QCD. Well, the number of kinematic variables would be the space-time X.
Right. Okay. Now it's clear to me.
Yeah, and you also see it. That's what I wanted to say here. You see, you have, this is maybe the notation you know. The mu sums over space-time indices, and the A is the one that, well, where you decompose into individual matrices. Okay.
Yeah, sure. Nice.
So just to follow up on that, if you could go back a couple of slides. One more. Yeah, that one. No, you passed. Go the other way. Yeah. So I guess the confusion is that in this equation, you've written A sub I, and you're using the same index I as the I on the X.
Well, it is. It is. You see, the A, there is for every, imagine I have, okay, let me clarify this point. My vector X is my vector of kinematic variables. So this could be, say, S and T. Okay? So X1 would be S, X2 would be T, for example. Okay? Then I can compute D over ds of my vector, which depends on S and T. It would give me a matrix which I call AS times the vector I. And the same for T. But now I would get another matrix, obviously, because I have another derivative. Okay?
Okay.
So now, of course, I can also write this as instead of using S, I use X1. So I write it as D over dx1 I being A X1. So let me call this A1 I, or D over dx2 I A2I, right? So there are two matrices, A1 and A2. And now I can also say, well, what is DI? DI is dx1, D over dx1 I plus dx2, D over dx2I, right? So that is dx1 A1 plus dx2 A2 acting on I. In this matrix, I call it A.
Okay.
Okay, so that A is equal to
Gotcha.
it's at this point just a handy way of writing things to compactify all the notations into one object. More questions? Okay, if not, then we can meet this afternoon at 2 p.m. for those who have questions, or if you want to if you need some background over things brushed a bit over, or if you want to have clarification on the lectures. And otherwise, we'll resume tomorrow morning at 10. Okay. Then I see you this afternoon or tomorrow morning.